Well, thank you all for coming. So for centuries, people have urged us to study ourselves as humans, to study our minds. And in more recent decades, computer science has offered a new opportunity, a new angle from which to make this study. And so that's what I'm talking about today. So basically, this approach to understanding ourselves really started with one person, Alan Turing. But I'll describe what he said and what he did not say. A very basic question which we all ask every day is every task that's doable by a human also doable by a machine? And he famously gave an answer to this. And in a radio broadcast, he said that in 3 sentences, it's customary in a talk or article on this subject to offer a grain of comfort in the form of a statement that some particularly human characteristics could never be imitated by a machine. It might, for instance, be said that no machine could write good English, or that it could not be influenced by sex appeal or smoke a pipe. It's an interesting grouping of 3 ideas. But then he went on to say, I cannot offer any such comfort, for I believe that no such bounds can be set. So basically, he told us that we should stop arguing about this. In principle, anything doable by a human is also doable by a machine. And well, we hear, we can see thousands of opinions on AI on the internet today, and the question is, how do we judge them? Well, one important point about his opinion is that his opinion was based on science. Okay, so this was an articulation of the Church-Turing thesis, which said that there's only essentially one kind of computation in the universe, and whether you execute it in silicon or in neurons, it's the same thing. So whatever you can do in neurons, you can also do in whatever you're implementing your computer in. So this question is resolved, but of course many others are not. So in particular, he didn't tell us how you should imitate a particular human capability by machine. And in fact, he didn't tell us what the human capabilities are. So my talk is centered on this question of, well, what can we define better what humans do? Okay, and the imitation game, this for which Turing is also famous for, of course, didn't answer this either. It made the important point that you should only judge a machine behaviorally, to judge what it does. But again, it didn't tell us what humans did. So what do humans do? Do we understand our capabilities? Well, probably we'd characterize our capabilities by some words like intelligence, and maybe that's the favorite word. But unfortunately, okay, so we use it all the time. So we talk about intelligence quotients, artificial intelligence, machines more intelligent than humans, intelligent life in the cosmos. So you would think we'd really understand this word intelligence, but when some psychologists were challenged to define it in the context of IQ tests, a report famously quoted that when 24 prominent theorists were recently asked to define intelligence, they gave 24 somewhat different definitions. So we don't have a definition of how do you recognize when someone is intelligent? What kind of things do they do? Of course, the origins of IQ tests follow from this tradition. So Spearman, who was a psychologist, he studied student behavior, student results in high schools, and noted that generally, although people did differently in Latin and French and geography, some did well in all of them, some did badly in all of them, and he hypothesized that the ones who did well had something which he defined as intelligence. But again, this is totally implicit, defined by correlations, doesn't tell us anything about what behavior you expect. So this is what I think we have to address to understand better who we are and what machines we should build. So for example, the word intelligence, I think, has helped us zero to make AI machines. But the word learning has been much more useful because it's something much more tangible which we can try to define. So, okay, so my approach, I asked a particular question, which I think is a slightly novel way of asking it. So I've also written a book with this cover. I'll discuss a notion called educability, which is something I'm defining technically here, but it's meant to remind you of education. And so the best part of the cover is what the cover design artist did. And he summarized the book by saying, how did we come in a few thousand years from being able to make an arrowhead to making, this is a cursor on a computer screen. So, so what was it in humans which enabled us to progress in a relatively short time? Okay, so no one believes that this change happened because our biology changed. Our biology didn't change. So with a very fixed biology for probably several hundreds of thousands of years, we progressed as far as our civilization without changing our basic hardware. So the question is, what is this basic hardware we have which differentiates us from other species? Okay. So the question is, what's the cognitive capability that enables humans to go from the arrowhead to the computer cursor? So I call this the civilization enabler. So it's a cognitive capability which enabled us to create civilizations, whereas other species have not done anything similar. And so one aspect of the way I define this is that I can afford to ignore many things which are other people's problems. So there are many capabilities we have. We've evolved for billions of years. But there are many capabilities which we share with other species, like vision, locomotion, emotions, long list. But I don't have to worry about these because other species have these in plenty also. I'm just trying to isolate what capability we got in a fairly short period of time when our ancestors diverged from the ancestors of other species. Okay. So the methodology I use, which I'll say a bit more about, is computer science, models of computation. And very roughly, what I'm dealing with is that I want the capability I'm defining to be defined mathematically, which means that it's I want it to be functionally well defined. So before you apply this capability and after, there's something has changed, so you have to define what's the change. It's like an input-output change. The other aspect is that this input-output change, I also want to make it computationally feasible. So there should be some explanation of how it can be accomplished in this universe with reasonable resources. I can't just write down anything. Okay, so this is a very old, the general topic of how we differ from other species is, of course, very old. There are hundreds of differences between us and other species, which academics study. But I'm looking for something specialized. This civilization enabler, it's a cognitive capability that is responsible for our civilization. So there are a long list of things people have said are important to humans. So tool use, we domesticate animals. So these are all important. Okay, but tool use isn't unique to humans. So that's not the answer. Animal domestication, important in our history, but again, there's no theory which says that if you can domesticate animals, then you can develop quantum mechanics. Okay, so many people emphasize that humans are special in that we're very collaborative, and social learning is learning from other humans. So we do that a lot. Again, these aren't unique to humans. Language, yes, we're very good at language, but again, there's no theory which says that if you have a language, like a computer may have a language, or you can teach an animal a language, that it makes them able to build computers. Varieties of intelligence, usually the problem there is that it's vaguely defined. So maybe one clue here is that it's implausible that this long list of items which various people put forward as distinguishing humans from other species. Of course, it's implausible that they all evolved suddenly in parallel, whatever. So it's more likely that we have some underlying capability which enables us to do all these things. So what I'll talk about is this underlying capability, which is a kind of a learning capability. So the question is, why are we so good at picking up information from the world? And so the suggestion is that we have this basic underlying capability, which I'll try to define more precisely, which has enabled us to do all these things. Okay, so as I said, many people have thought about this. What did Darwin say? So Darwin said that if you look at these fairly conventional items and many other words which people think of in this context, then he said that, well, none of these are, all these things we differ from other species in degree and not in kind. So there's nothing you can find which is humans can do absolutely and which animals can do not at all. So he couldn't find any, and I think this judgment is true today. So what are we up to here? So what we're up to here is that with these computational models, we can define things more precisely. And the advantage of defining things more precisely isn't that we get such an incredibly precise science, but it's that we can define things a bit more complicated. Okay, so we're not restricted to single words from the standard dictionary or a phrase. We can build up a slightly more complicated hypothesis just because we're more precise. Okay, so it's as simple as that. It gives us a more precise way of expressing ourselves, so we can express things which are a bit more ambitious and things which in Darwin's day would have been very hard to write down because there just wasn't the right language or scientific context. Okay, so I'll now just tell you what my proposal is, and then I'll talk about this, talk around what it may mean. Okay, so the proposal is a combination of three different things in some context. Okay, so it's not a one-phrase thing. So I call this capability educability because it reminds me of the human being's ability to soak in information. So people are either listening to a lecture or they're looking at their cell phones, they're soaking in information from somewhere. And so other species don't seem to be able to do this on quite the scale. So the question is, how exactly do we soak in information? So I say it's three different components, all integrated in a certain context. So the first component is being able to observe and generalize from experience. So this is like learning by example. And so this I will identify with exactly the capability which is currently being exploited in AI. So current AI is essentially exploiting this on a large scale and almost nothing else. But this isn't quite enough, so that's why, what do we add? Well, the second part is that once we've learned something, we've learned to recognize something, we should also be able to combine what we've learned and kind of reason with it. Okay, so if you have to solve a problem of how you go from here to somewhere else tomorrow, you may have to combine different pieces of information you've learned at different times. So this is combining things you've learned. This is applying knowledge you've learned from example. And the third aspect, so all these I'll say more about, is that we can also acquire knowledge, beliefs, which are explicitly described to us by others. So the context is that I can, if you're in a class on, say, quantum mechanics, then the instructor can give you a formula, and you can remember the formula, you can execute the formula, evaluate the formula, but the point is the formula you don't have to derive from your own experience. There are some other people who did some very laborious experiments in quantum physics who made observations and generalized from their observations, and then it was very easy for someone just to tell you what the generalization was. So certainly this third aspect is a very human aspect, that we share information extremely efficiently once it's been derived from experience. Okay. So I'll say more about all these things, but the important thing is that all this has to be done in a rich enough context, which I'll say more about again. So the fourth part is that we can analyze the world we can analyze a scene with in some detail. I can say how many people are sitting in the second row there and who's sitting next to whom. And so this is a kind of level of description which people in AI tried to do in the 70s and what logicians have done for much longer. And the idea is that this is necessary. You can't bypass it. The last part is symbolic naming, which for computers is obvious. The idea is that you can assign an arbitrary name to some concept of interest. So in the animal world, your dog recognizing its own name is a very basic implementation of symbolic naming. You can name your dog anything. But for animals, it's quite, non-humans, it's quite hard. It's believed that there are few species which can even be called by their name, by their individual name. So dogs can, a few other species. Okay, so this is for human brains is a big deal, but for computers it's kind of obvious. Okay, so this is a definition. It's a technical definition, and I claim that this is the integrated. With this integrated, gives you a powerful machine in your head by which you can absorb information, kind of analyze it, make plans, and act. Okay. Not much on educational philosophy, but just to say that I suppose the number 3 is the very classical notion of learning by instruction. The first one is hands-on learning, and second one is applying what you've learned. So clearly all these 3 things are good things in education, and here maybe the point is that you need all 3. So I don't need to speculate when all this happened in evolution, but the main point is that, I think, is that just generalization is very ancient in evolution. Animals swimming in the sea have to figure out where the food is, and that's how they do it. And probably the whole combination only arose at the beginning of our species, maybe 300,000 years ago, or maybe earlier. Okay, so I'll just go through the points again. So generalizing from experience, I identify with exactly what machine learning does today, which is that you have a learning algorithm which is fed with examples of something like pictures, and these are labeled by whether the picture contains an elephant or not. And this learning algorithm outputs a classifier, which is another algorithm, and this other algorithm will look at new pictures and tell you whether it's an elephant or not. And so this probably approximate correct model of learning makes a quantitative model out of this. And the main point is that you want to make sure that your generalization is accurate enough to be useful. And how this is expressed is by the idea that the more effort you put in, you should be rewarded by making errors less and less often. And it should go down fast enough. So this is an algebraic power. It could be like 1 over square root of n or 1 over the 10th root of n. So the point is that this rate of decrease is good enough that it gives you some reward. So another way of saying it is that if you do this, and then if you put 10 times more effort in computation, suppose you halve the error, then the promise is that if you make 10 times more effort still, then you'll halve the error again. So this is like being so it's often some sort of addiction for machine learning. So the idea why companies, once they've invested $1 million in training a net, they're tempted to invest 10 million and then 100 million is naturally explained by the fact that so in certain theoretical algorithms, you can prove that they really learn this efficiently. And in practice, if you plot how efficiently successful machine learning algorithms work, they follow these laws. Okay, so this is still learning by example. So back learning is the formalization of it. Important point is that in the definition I just gave, it only promises you generalization. So it says from examples of elephants and non-elephants, you can generalize new examples. If you describe a human phenomenon of learning, you're tempted to list a whole lot of things which humans can do besides generalization. And people complain that, so these are all words which machine learning experts will recognize. People complain that these aren't given you for free. And of course, the answer is that the algorithms used for learning are winners in this game of generalization. And they're not, they don't promise you all the other things. But all the other things are important. And they point to the fact of why we need to do more. Okay. And so doing more is going to 2 and 3. So as I said, chaining beliefs is important once you've learned once your little fish on the bottom of the ocean has learned to recognize where the food is, it may want to chain together various pieces of knowledge it's learned. And here the main requirement for a system which can do this, besides, again, computationally being feasible, is that, this is a word borrowed from standard logic, is soundness. So soundness means that if you combine two claims according to some given rules, then you should believe the conclusion. Okay, if A implies B and B implies C, you should believe A implies C in most logics. Okay, so you need to be able to simulate this, and the kind of realization is something like this, that if you chain together two rules which you've learned from experience and you believe in them 99%, then you should believe in the conclusion when you chain them together to some accuracy, maybe 98%. But it shouldn't collapse to 0 or to 3%. You should have some lower bound on how much you can rely on combinations. And just one thing you can do with this robust logic is explain this phenomenon. So if I ask you, did Aristotle own a coffee-making machine? Then most humans can answer this. And in fact, now most large language models can answer this too. And of course, the paradox is that these learning machines weren't trained on examples of Greek philosophers and their domestic appliances. Okay, so you think that for a machine to answer this question, you need to feed in lots of examples of Greek philosophers and what they owned. But you don't, because the machines can already do a bit of reasoning. So humans and machines can answer this by chaining together things they've learned independently. So this is the kind of thing which the chaining together has to explain and does. Okay. So the other thing, the context, is that the world is rich, so crows can solve hard problems with seeds in glasses and figuring out that you have to put stones in for the water level to rise. So the world is complicated because there's a seed, there's water, there's a glass, there's a water level, complicated relationships, and somehow an AI system can't take shortcuts in this because all the details are relevant. So this is the context I mentioned in which all this has to be realized. And so how it's realized is, this is part of the formalism of robust logic, is that, for example, you've got these tokens, your eyes shut, you think about something, you think about your dog, and then you think about something which your dog likes, and you want to think what does my dog like? And in your brain you'll have some rules which you've learned, and these rules will predict for you, whether maybe your dogs only like bones. Okay, so these rules aren't like standard logic, but they're basically things you've learned. It could be some deep neural net, which predicts whether something is a bone. And okay, so and this is what happens in your mind's eye. So this is a formalization of working memory in the language of cognitive science, but we have to formalize it. Okay, so so quickly, what is reasoning? So this mechanism provides a chaining mechanism, but I'm not defining what reasoning is. So no one knows what reasoning is. Reasoning is almost as bad an idea as intelligence in that we can't pin it down. There's no one way of doing reasoning. So what's done here is that here you provide a general chaining mechanism, and then different kinds of reasoning you have to do with different rules of inference. So for example, we can all do arithmetic. We spend a lot of time learning it in school, and it's a method of reasoning. Someone had to invent it, we have to learn it, then we can apply it. So reasoning is like multiple different kinds of reasoning which a single mechanism can realize. Okay, so the third part of this is educability is being able to execute a program or a recipe given to us explicitly by someone else. So this is kind of a lecture room style learning where someone tells you some theory which you can interpret in your minds. So your interpretation here, the theory, this just depends basically on the universal Turing machine. So educability is the integration of these three capabilities. And of course, the point of this third part is that it allows discoveries made with painful and costly experience to be shared, which humans do so successfully. These discoveries can be very powerful, like new ways of reasoning. So someone discovered arithmetic, it's very useful to us, and we teach each other fairly efficiently. And so other species don't seem to do this. And this is how science works. This is how we get complex cultures. And I think this is some explanation of how efficiently we can make discoveries, spread it very fast in a population. We can make further discoveries, and this is how technology can advance and change. So this is basically a definition of educability. So in pictorially, one way of summarizing this is that this basic learning from experience, this back learning, and also robust logic applied to it, is like adapting yourself to the world. So if you're a fish in the ocean, you learn where to find food, where light comes from. So there's some actual environment, and you learn to adapt to it. So there's some reality. So once you're able to acquire instruction from someone else, someone gives you a story, then there's no guarantee that that's grounded in reality. Of course, why science is successful is that we trust. So if someone gives you a lecture on quantum mechanics, you believe the instructor is truthful, and that everything he's telling you is plausible, based on the best evidence. But it could just be lies. Okay, so somehow we humans, with this extra capability, are let loose in a world which gets more risky in a direction which other species is not so risky. Because we can take in information which is, we can take in information very efficiently, but nowhere in the definition is there a part which tells us, whether to believe the information, how reliable the information is. That's much harder to evaluate. Okay, so important point is that educability has many parameters. So you shouldn't think of, like superintelligence. It's some single capability, and we'll make a machine and declare it to have been achieved. So even with standard machine learning, there are many parameters. I mean, for example, the main parameter is the data you train it on. If you train a machine learning model on different data, you get different outcomes. So with educability, there are many more parameters. So for example, if you have an independent system, then a very basic question is, who should it trust for new information? Who should it believe? So humans have sophisticated methods of deciding this. So psychologists have studied this. If we have standalone machines and agents, then this will be an important parameter. And there's no one good answer, because in a very truthful world, it's good to be trusting. In a very non-truthful world, you should be more cautious. So there are several other strategies which I don't have time to describe, but this mind's eye I described, there are many parameters there, like how often you refresh it. So in this system, there's also room for kind of creativity, where you consider new combinations of things which you already know. And how exactly you do it is, again, a parameter, and again, we don't know what's the most fruitful. Different things may be fruitful in different contexts. And what reasoning methods you teach your machine, again, that's a parameter. So having parameter is not a bug in educability. I think it's a feature of cognition. So the fact that we're all different, we're experts in different things, is maybe it shows the fact that there are many parameters in this game of being educable. So these usual arguments for the fact that we'll get these super intelligent machines and then we'll be extinguished, I think those are fallacious. I think what we should be doing is to try to express our capabilities in kind of prosaic, explicit, understandable computational terms, like I've tried to. And in that case, these things are less frightening. So it may be that at any one task, these machines will be better than I am or you are, but that's okay. I mean, it's not so frightening. chess programs are better than humans. This hasn't extinguished humans. In fact, it hasn't even extinguished human chess. People still play chess. Okay, so that's okay. So I'll just give a summary now. So educability is a proposal about information gathering capabilities. It's expressed in terms of prosaic notions. It has many parameters, which are, I think, inevitable, and we should understanding the whole range of possible versions of this educable system, just like there are lots of versions of human knowledge, is something which we should appreciate and understand. And this also provides some specific goals for better AI. So thank you.
Thank you, Professor Valiant. And now I would like to invite Professor Kedar up to moderate the Q&A. Professor Kedar, please.
Thank you very much. Good morning, everybody. Really exciting talk. It's the first time I've heard you speak, and it was, for me especially, incredible how you're able to conceptualize these concepts. And the first question that popped to my mind, and perhaps I can take the liberty of being the moderator and ask the first question, is how do you then take this sort of understanding, develop this theory, and formalize it into something like the PAC model, for example?
Well, in some sense, it's already formalized because it consists of parts which are separately formalized. But when you talk about a formalized theory in computer science, you tend to think of kind of one model. Mm-hmm. And here the difference is that there are many parameters, and that's okay. So if you buy we think of computers as being one model, Turing machines, which is the right way of looking at it. But of course, if you buy a machine, you have to decide how much memory to buy and how much what speed to buy. Okay, so again, here it's these parameters proliferate.
All right, so I think people are lining up, so I'll just encourage folks in the audience. There are mics in both aisles, so please come up, introduce yourselves, and ask your question.
Hi, I'm Eric from Lund University in Sweden. Thank you for a fantastically interesting talk. So you talked a little bit about reasoning and different ways of doing inference. And when hearing about your definitions of educability, it seems to me intuitively that causality is important. I wonder if you think that this is the case, and we therefore need kind of a paradigm shift in current artificial intelligence where correlation is kind of the way of doing inference.
Yes, so if you notice the slides which were flying by a bit too fast, so causality was one method of reasoning I had. So probably I suspect that when we're born we have some capabilities for dealing with arguing about causality, but also it can be greatly improved by being educated. So certainly everyone understands that causality is a very important method of reasoning, which we use certainly in science, but also in everyday life. Yeah, so when you say that current AI is based on correlation, well, so the basic PAC model you can say is based on correlation, but of course when you use it to do an LLM, then you are learning patterns of reasoning exercised by humans. So so LLMs do some amount of reasoning rather unreliably, and these are based on patterns which they pick up from humans. So when they pick up a human arguing about causality, then LLM can sometimes pick that up. But I think you're right. But in some sense, I think that causality is a second. I'm treating it as a second-class citizen in the sense that it's a very important kind of reasoning. I don't think one can put it as kind of as the prime mover, which I don't think it is. It's just a useful method of reasoning.
All right, thank you.
All right, our next question.
Good morning, Professor. So my name is Adolphus, and I'm from the Singapore Nuclear Research and Safety Institute. And I essentially only have one short question. So when it comes to learning, especially when learning based on limited information, there is a need to essentially characterize the uncertainty as well from these models. I just want to hear from you, in your opinion, how may we actually characterize such uncertainties?
Yeah, so you mean that if a machine makes a prediction, it should also give you some probability of some confidence?
Indeed.
Yeah. So in all the things I prove about in pack learning and in robust logic, I mean, that goes hand in hand because, so the idea is that we try to learn to recognize all concepts in the English dictionary, for example, from examples. But for some, we may not have seen enough examples. And so we know that we have not succeeded. We don't understand a certain concept. We've never been told about it. We haven't seen any examples. So every act of learning in this pack setting is based on how much evidence there's been to support a conclusion. So basic pack learning, you can you can do a statistical statement about how confident you are. And then when you do the robust logic, again there are arguments for bounding from below the confidence you should have. But of course the proviso in all this is that you're making some assumptions about the world. So for example in pack learning and any machine learning, you're assuming that the world hasn't changed from the data it's learned from. Okay, so all this is based on some assumptions about the world not changing and being benevolent in other ways mildly. So by nature, I think that machine learning and everything which derives from it has a kind of a statistical basis that it's going to be accurate on the average, but in a single instance, it's limited to what extent you should have faith in what it's telling you. There are no absolute guarantees on single instances. Okay.
Thank you so much, Professor.
Perhaps linked to that, I was wondering as well, the field of Bayesian statistics is essentially based on some prior distribution and predicting a posterior distribution. And so it's all probability distributions, which even in physics we encounter quite a lot because given the quantum nature of things, electrons don't exactly belong in a location, but it's a probability distribution. And you can then still predict certain things based on that distribution. So how is that then linked to, let's say, the probability approximation correction?
Yes, good question. So in most applications of probability theory, you kind of know what the distribution is. So physicists know what the distribution is. Right. In Bayesian reasoning, you hypothesize some distribution. So the main issue which which is hidden behind all this, what people don't make explicit, is that when you talk about common sense knowledge in the world, the distribution is just too hard to learn. Mm-hmm. So in some sense, almost recognizing an elephant is easier than to actually describe the distribution of elephants. So these are all shortcuts. But amazingly, many of these things do work for all distributions, which you don't, even without you knowing it. Okay, so as long as you train and test on the same distribution, it works, even if you don't know what the distribution is. And theories where you analyze the distribution just become computationally too hard. So Bayesian reasoning has the limit that it's not computationally feasible on a large enough scale.
Interesting. Okay, we'll take one question from...
Hi. Yeah, hi. I'm Nigel from DSO. My question was regarding that you brought up this concept on mind's eye from cognitive science, right? But there's also a similar theory called the theory of mind, where you have to think about what other people are thinking about, and I'm not sure whether that fits your concept of educability. Yeah.
Yes. So I think my notion of this mind's eye is just a very basic computational framework of dividing up the world and having rules, and so it's primitive. So one particular instance you could use it for is to think about other people and how you relate to them. So I think that would just be an instance. But I need to formalize in very simple terms things which many people discuss, psychologists. So in some sense, attention, in the sense of transformer architecture, is a kind of heuristic which tries to do something about this problem. But I need to make very explicit what the problem is, okay? And there are many instances, and many people discuss similar concept. But I need a particular computationally feasible version of it.
Yeah, because linking back to Prof. Kedar's question about distributions, right? So theory of mind is one of the ways in which we can try and detect like out of distribution like concepts, because for LLMs, usually they just accept whatever that's given to them regarding like facts in or like wrong examples during your prompts. So I thought that would be something that's good to include in educatability.
So something which includes
like learning to detect from out of distribution, like something that's contrary to your internal world model. Yeah.
Well, I think so. All these things that you've learned from examples from some distribution. The LLMs work from whatever data is fed. And then the only guarantee is that it's going to work well on similar distributions. So the out of distribution in like my example with the Aristotle thing. So I think many cases of really out of distribution things I think we just can't do. But many things which look like out of distribution are things where they're in distribution, where we have to link together two different pieces of knowledge which we've learned in distribution, but this combination, like this Greek philosopher owning his coffee-making machine, maybe out of distribution, but we can argue about it using facts we've learned in distribution. Okay. So I think certain aspects of out of distribution things can be explained by in distribution phenomena, and certain others probably cannot.
Okay, thank you.
We'll take one last quick question because I have a red flashing light here that says we need to stop.
All right. Hello, Professor. Thank you for your thought-provoking lecture. My name is Anna from Seoul National University, and my question is probably cliche, but personally I haven't heard much discussion about it. So you mentioned that Alan Turing stated with quite certainty that machines can replicate anything, even being influenced by sex appeal and smoking a pipe. So if with certainty they can replicate all human capabilities, what's stopping them from inheriting all of our vulnerabilities as well, like irrationality or emotional fragility? And how can we manage that when we are so bad at managing our own?
Well, I don't think we should make machines. Actually, Turing said the same thing, that just making machines to be exactly like us, there's probably no point. So you shouldn't make machines whose behavior you don't like. So I think we'll probably, make machines to simulate different aspects of our behavior, and just making a machine which, in every respect, is very human. So basically, Turing said that that's just in bad taste to even try to do that. So he rejected it on aesthetic grounds.
Thank you. But are we really able of controlling that? I mean, past a certain point, isn't it kind of out of our hands? Or once they develop a consciousness, or yeah.
Well, I think we'll make machines to do different things. Then the question is, do we give control to them over ourselves? So I think need to use the word control is the important thing. So we don't care what they do as long as they're out of our control. Of course, if we give them control, then it's easy enough to give them a stupid machine control which does something very bad. But I think, but what I disagree with is the argument that machines will necessarily grab control from us. I don't understand that argument.
I see. Thank you very much for your answer, and I look forward to future lectures as well. Thank you.
A great discussion that please, I think Prof Valiant is going to be around later on during the tea break after the next lecture. So thank you very much again for a wonderful talk.